All right, guys. So next, I want to just introduce residuals to you. Um, we've talked about them a lot. We've talked about a lot of things going on, and I know there's some typos on this page. We're going to get those fixed. This goes without saying. If you see typos throughout any of this stuff, just let me know. It's not a huge deal to me. There's a lot of formatting issues, and like I've told you from the beginning, these are my personal notes. So some of the times I get going really quick, and maybe don't finish a sentence, or there's an extra character hanging out or something like that. Just let me know and we can get them cleaned up for you. But what I try and do is I try and give you the stuff I learned it from, the stuff that I think about it from, not something that's kind of preformed, because I think that can be harmful to the education process sometimes. But a lot of, there's going to be little things here and there, but for the most part, everything's clean. Some of it could be the transition into the online platform. Just let me know about that. And you're going to see some of that on this page, and I'll tell you to ignore some of it for right now. And it should be cleaned up by the time you get it. What we want to do is we want to talk about the residuals, okay? Now, here's what the residuals are. The residuals are just our myths. We talked about that from the opening, but we want to talk a little bit more about multiple linear regression and the assumptions, because diagnostics are a huge piece of what we do. Diagnostics mean your inference could be right or wrong, so we want to make sure we're making the right inferences and we understand where it comes from. So the first thing I want to talk to you about is, just the major assumptions. We say y equals x beta plus epsilon. The variance of the residuals epsilon given x is equal to sigma squared times in. Notice, we're not saying anything about normality. We're not saying anything like that. That's actually a very strong assumption, and you don't have to make it most of the time. But here's our ordinary least squares estimate, x transpose x inverse, x transpose y. We talked about that a little bit last module. But let's break it down. What we can then do is look at y hat, which is x times beta hat. Y hat are our predicted values, the points on our line or the points on our hyperplane in multi-dimensions. We can break that down into a piece. We say x times x transpose x inverse, x transpose y. What we can do is we can call this right here the hat matrix. Now, the hat matrix is a projection matrix. It takes y to y hat. That's what I want you to think of, okay? Now, it turns y into y hat. So we have h times y. Now, we call h the hat matrix because it puts the hat on y. H times y puts the hat on y. It's fifth grade, or it's kindergarten type stuff, I know, but it's one of the things to remember. It allows us to come up with the predicted values for y. Now, there's a couple things I want to talk to you about the hat matrix that I think are pretty interesting, but one of the last things we need to know is we know the residual is y minus y hat. What that's really equal to is I minus h times y. Now, what matters about that? Well, what we're saying is the expected residuals, the expectation of the residuals is equal to 0. What that means is when we fit this model, when you do your OLS estimates, if you sum up the residuals, they're going to equal 0. So a lot of times the mean of the residuals is going to be 0. Now, notice there's a difference here. We're saying the variance of epsilon given x is equal to sigma squared times in. That's the theoretical assumption. The practical assumption you're going to see is the variance of the estimated epsilons, okay? The actual observed residuals is equal to sigma squared times IH. And that comes from this piece right here. Sigma squared, it becomes sigma squared times I minus H. So what this becomes is, it becomes a way to look at how residuals are correlated. It's not a huge deal unless all of these things are very large. Now, looking at an individual residual, we're going to have that the variance of epsilon hat is equal to sigma squared times 1 minus HII. That's what this piece right here breaks down to. Now, this HII is what we call a leverage, okay? And you'll hear me talk about leverage more and more and more in this section. But the entire thing is, a lot of diagnostics break down into two pieces, the residuals and the leverage, okay? You'll hear me talk about it when we talk about outliers. You'll hear me talk about it when we talk about influence. All these things break down to that piece right there, this HII, this leverage idea. Now, we hope that the variance of epsilon hats behave like the assumption we're going to make on the epsilons, okay? So there's a lot of things to think about. There's a lot of things to talk about in this. I just want to give you some ideas on the hat matrix. It's something we need to understand, and here's just some basics of it. What I really want to give you is this piece right here. Here's, H is symmetric, n by n symmetrics, H times X equals X. You can prove that to yourself. I minus H times X equals 0. H squared is equal to H times H, which equals H. This is orthogonal projection, so on and so forth. This is all the linear algebra stuff that you don't need immediately. But what I want to show you here is this. we can directly define the elements of H by this equation. Now, one way to look at this is we call this Mahalanobis distance, okay? Where you can think of this as the distance between xi and xj divided by some variance structure of x transpose x inverse, right? We were told to think about that as the variance of y, or the covariance matrix, the variance of x, or the covariance matrix of x. So what we're really doing here is looking at the sum of squares, okay? Or x1i times x1j plus x2i plus x2j, so on and so forth, divided by some structure of the variance here, okay? That's what you're going to see. Now, one of the things you can think about this is the distance between xi and xj. But for the ith term, it becomes a little bit more important. For the ith term, it becomes a little bit more important because what you're going to see here, if we come down here and just look at hi, it becomes 1 divided by n plus xi star minus xi bar transposed, the centered versions of the x's, times xi star minus x bar. So HII can be thought as xi's distance to the mean of the data. That's why this is so important. It tells us if something is an outlier in the x space. Just the diagonal elements of the hat matrix, guys. Just the things running down the diagonal. Just those HIIs. So it tells us if something's an outlier in the x space. Remember when we talked about it at the very beginning of this class? We said, look, there's outliers and there's leverage. HII becomes leverage. It measures distance to the mean of the rest of the data. If it's large, that's going to cause issues for us. Now, just some other things to remember. Just some other things to remember. HII is bounded between 1 over n, that says all x values would be the same, or 1 over r, the number of replicates you have of that same xi value. And it's also bounded above 1. So these are all the different things you're seeing. These are all the different things we're talking about when it comes to the hat matrix. Now, it becomes fairly important for you to remember this about leverage. This is a key point in everything we're going to talk about moving forward, okay? You're going to see it come up really big at the last part of this module, so it's something I want you to keep in mind, all right? All right, guys, let me know if you need anything.